Hello friends, so this is the last lecture on this series of lectures on refrigeration cycles in our module number 9. In the previous 3 lectures you have been introduced to the compression based refrigeration systems. Particularly we have discussed about the vapor compression refrigeration cycle, where we have an evaporator where the refrigerant picks up the energy from the space which we want to be refrigerated and it gets converted to vapor, generally saturated vapor or in certain occasions can be superheated vapor, and subsequently we compress that vapor in a compressor so that its pressure and subsequently the temperature level rises, so that its temperature becomes higher than the surrounding temperature, and accordingly it can reject the heat to the surrounding in the condenser. So, we have discussed about different variations of the vapor compression cycle in the previous lecture, like the use of multi-staging, multiple compressors, the application where we are looking for extremely low temperature refrigerations, and also we have discussed about the gas based refrigeration cycles, where there is no phase change, rather it is just the reverse Breton cycle, where the working medium remains as gas throughout, and therefore, instead of having an evaporator and condenser, we basically have two heat exchangers, one where the working fluid, the gas, picks up the heat from the refrigerated space, and other where it rejects the heat to the surrounding. Just the way we analyze a Breton cycle, quite similarly we can analyze that gas refrigeration cycle as well. I have probably mentioned the name of the Stirling refrigeration cycle, which is the reverse Stirling cycle. If you are interested, you can search in the books for the same as well. Now, today I shall be talking about another kind of refrigeration system, which is again vapor based, but not a vapor compression one, because there is no compressor at all. The biggest issue in vapor compression refrigeration system is, though I have to mention that that is the most popular one, about 85-90% of the application of refrigeration or cooling, whatever you can find, that generally belongs to this vapor compression category, or in certain conditions like the aircraft applications etc., the gas compression based refrigeration systems. However, the new one that I am going to talk about, where there is no compressor, but it is still vapor based, that is I should not say that is a new technology, because the technology is also quite old, but because of certain shortcomings of this, it has not been achieved that much level of commercialization. But over last few years, particularly with the focus of global warming and other environmental effect caused by synthetic refrigerants etc., this one, which is actually a green technology, this is coming up in big time, particularly for large scale application. When we are looking for very large scale refrigeration, like centralized air conditioning for a shopping mall, or centralized air conditioning for a big theater, there this kind of system is quite profitable. So, that particular system is known as vapor absorption refrigeration system, or VAR system. Like the vapor compression refrigeration is VCR, this is the VAR, vapor absorption refrigeration system. And as the name suggests, here instead of compressing the vapor, we are actually going to absorb the vapor. Here the compressor part, like in classical vapor compression refrigeration system, you have 4 components. We have one evaporator, where we have to pick up the energy from the refrigerated space. We have a condenser, where the vapor is going to reject the heat to the surrounding. We have an expansion valve, where the pressure of the vapor is going to drop from the condenser pressure level back to the evaporator pressure level, and subsequently facilitate the change in temperature or lowering its temperature. But there is a fourth component, which is the compressor, which is the work consuming component. In vapor absorption system also, the other 3 components, that is the evaporator, condenser and expansion valve, remains as it is. However, the condenser is replaced by a combination of several other components. The arrangement is such that we use a second material, the refrigerant of course will be there, plus we are going to introduce an absorbent or an absorber, and that refrigerant is going to get absorbed in the absorber, and subsequently the operation whatever we get from the compressor, that we are going to achieve by some other means. Just think, what is the function of having a compressor? The function of having a compressor is to compress the vapor, of course. But why you want to compress the vapor? Because we want to raise the pressure, we want to raise the pressure of the vapor from the evaporator pressure level to the condenser pressure level, such that the saturation temperature corresponding to that condenser pressure level is higher than the surrounding temperature. So, the ultimate aim of having the compressor is to gain this rise in pressure, or to change the pressure from this evaporator level to the condenser level, and any option of achieving that is welcome. and particularly if we can devise something where the work input requirement for the compressor can be substantially reduced, that is definitely very much desirable, and that is why we have this. Ammonia and water are written here. We do not need to focus that much on this, but or on this combination, because we are going to talk more on this. But here just think here there is a big rectangle covered by the dotted line. What components we have outside the rectangle? We have the condenser, we have the expansion valve, and we have the evaporator. In the evaporator, your refrigerant is picking up the heat, is QL, or maybe as per our terminology Q dot E from the cold refrigerated space. In the condenser, it is rejecting Q dot C as per our terminology to the surrounding. In the expansion valve, pressure is dropping from the condenser pressure level to the evaporator pressure level. On this side, on the upstream to the expansion valve, the pressure is the evaporator pressure level, and the downstream, sorry, I should have written the condenser pressure level. On the downstream, it is the evaporator pressure level. So, these three components are doing their normal operation only, but the compressor which we should had on the exit of the evaporator and the entry of the condenser, that has been replaced by this big rectangle. Now, what we have in the rectangle? Just look at it component wise, starting from the evaporator exit. Here the working medium, or sorry, the refrigerant that we are using, that is ammonia, one of the natural refrigerants. That is one big advantage of vapor absorption system, is that we can easily use the natural refrigerants like ammonia or water vapor. Now, this ammonia vapor which is coming out of the evaporator, normally saturated vapor or maybe slightly superheated vapor. Now, that we are taking to a big chamber known as the absorber, and in this chamber we have water or maybe a low concentration solution of ammonia, aqueous solution of ammonia, that is an ammonia water mixture. Once ammonia comes in contact with this mixture, it also get absorbed in this, and during this process we generally have heat rejected to the surrounding. Therefore, we need to have some kind of cooling jacket, so that we can maintain a low temperature in this, and also we can continuously remove the heat that is being generated when ammonia or gaseous ammonia gets absorbed in this mixture. So, this component is called absorber, because the ammonia is getting absorbed in water or maybe in an aqueous solution of ammonia to produce another solution with higher concentration. So, initial solution that we had, that is low in ammonia concentration, and after this ammonia coming from the evaporator that gets absorbed, we have another solution with which is having higher concentration. Let us give some name to the states. Let us say this is our state number 1, 2 at the exit of condenser, 3 entering the evaporator, then 4 coming out of the evaporator. So, we are calling this state as 5, where we are having a aqueous solution of ammonia with quite high concentration of ammonia. Now, we are having the pump, and in this pump we are causing the change from this evaporator pressure level to the condenser pressure level, just what we did in the compressor. Now, in the compressor, what is our working medium? Our working medium is a vapor. So, we know that this being a steady flow kind of device or an open system, the work input requirement W dot in, or maybe just W in, let us remove the rate, is generally represented as integral of minus V dP, starting from the evaporator pressure level to the condenser pressure level. If these two pressures are same, that is PE and PC remains same, then the magnitude of this input work requirement definitely depends on the specific volume of the working medium. Now, in vapor compression system, what is your working medium? You are working with vapor, saturated vapor or superheated vapor. So, its specific volume may be Vg as per our notation if it is a saturated vapor. When you are talking about this vapor absorption refrigeration system, what you are working with? We are working with an aqueous solution of ammonia in this particular case. So, you are working with some liquid, and if we term this as liquid, it is an aqueous solution of ammonia in this case. Now, out of these two specific volumes, which one is lower? Definitely this V liquid is much lower than Vg, it can almost be negligible compared to this. Then which one will require less work input? So, definitely the work input requirement for the VCRS is significantly greater compared to the work input requirement for the VARS, or we can say the other way, the work input requirement for the VARS, where we actually have a pump or a solution pump, that is significantly lower. So, the mechanical input requirement to this cycle is much lower. Then what else is happening? The solution which has been pumped to a higher pressure, to the condenser pressure, now goes through another component which is known as a generator, another compartment which is generator. In between we may have a regenerator where we are using some residual heat to rise the temperature of this. So, the state is 6 coming out of the pump, and then after the regeneration we have the state 7. For the moment you can ignore the regenerator. So, it is entering the generator, and in the generator we are adding heat, where the heat can be coming from some waste energy source, maybe solar energy or whatever may be the source of energy, but something which is capable of rising the temperature of this solution to something around 100 or 120 or 140 degree Celsius, not more than 180 degree Celsius. So, we do not need to go to very high temperature, we need some source of energy which is able to rise the temperature of this aqueous solution of ammonia to that levels. And generally any waste energy sources or maybe solar energy or sometimes geothermal energy, just maybe the exhaust gas coming out of some automobile vehicles, that has sufficient amount of energy to raise to this temperature. Like in this diagram, it is shown in the form of a solar flat plate solar collector, where the water is absorbing solar energy and then that is circulating through the tubes that are shown here. It is passing through these tubes, and as it this heating jacket is passing through the solution, it is adding heat to this. So, this Q gen, or as we let us write as Qg, this amount of heat is being added to the generator, and as heat is being added, then ammonia will get separated from this, will get liberated from the mixture, and the gaseous ammonia will be will come back, and that is going to go back to the condenser for this. Generally ammonia and water vapor both are quite evaporative in nature, and therefore, we need this rectifier so that we can separate out the water vapor and send the water vapor back to the generator, and only pure ammonia is allowed to go to the condenser. So, ammonia has got separated, and then what we have left in the generator on this line as state number 8, what we have left? Ideally it should be only water vapor, but truly speaking it is not water vapor, it is a low concentration aqueous solution of ammonia that is generally at a much higher temperature. So, we have a regenerator where it gets cooled to get converted to state 9, and while it is getting cooled, it adds energy to the other stream that was coming, the stream with higher concentration. Then we have the expansion valve where the pressure again falls from this condenser pressure level back to the evaporator pressure level, and finally back to your absorber with state number 10, where this low concentration solution is coming and getting mixed with the pure ammonia coming from the evaporator again to form that high concentration solution. So, what are the inputs that you are giving? Your output remains the same. Your output in this case is this QE or Q dot E. What is your input to this system? Definitely your input is the pump work that you are giving, the or power that you are supplying to the solution pump, plus there is another input. We are also giving this Q dot G, the energy, that thermal energy that you are adding to the generator. So, it is more like a thermally driven systems. Instead of having mechanical energy, we are definitely giving mechanical energy as the input in form of the pump work, but that is generally extremely small compared to the work required for the compressor, and that is why it is more a thermally driven system, or we call it a thermal compression that is happening to the working medium. So, ammonia water mixture is a very common kind of working fluid combination that we use. Here we are using two fluids. One is the refrigerant, which is ammonia, and other is the absorber or absorbent, which is water vapor. In this case there can be several such combinations, like we can also have a very popular combination where water is used as the refrigerant and we use lithium bromide as the absorbent. That is also a quite common or popular solution, and similarly we can have a few other mixtures as well. So, if we quickly want to perform a mathematical analysis or thermodynamic analysis for the system, if we take this is your vapor absorption refrigeration system, then what are the amounts of energy that you are giving input to this? Of course, Q E or Q dot E is input to this, and also Q dot G is the thermal energy that is giving input in the generator. From here heat is being rejected in the condenser, and also heat is being rejected in the absorber, plus we are having the pump work as the input. So, if we apply first law of thermodynamics on this. Then as this device is working over a cycle, so we know that cyclic integral of del q is equal to cyclic integral of del w. Correspondingly, in written in rate form, we can write that total amount of energy given as input, that is q dot E plus q dot G will be equal to q dot C plus q dot A plus w dot P. There is a total amount of energy that we are giving as the input, or we write this as q dot C plus q dot A is equal to q dot E plus q dot G minus w dot P. So, this is the first law form. Now, let us look at from second law perspective. From second law point of view, we know that total entropy generation over this cycle has to be greater or equal to 0. In the ideal case of a reversible process, it is equal to 0, otherwise entropy will always be getting generated. That is, the total change in entropy for the system plus change in entropy for the surrounding, this combination has to be greater or equal to 0. Now, here the system is working over a cycle, and we know that for any cyclic process the change in entropy is equal to 0, because the system is always keeps on coming back to the same point. So, delta S system is 0. So, for this process to be realistic, the total change in entropy for the surrounding has to be greater or equal to 0. If it is a reversible process, the surrounding will be restored, and so the change in entropy for the surrounding also will be equal to 0, but for irreversible process the entropy of the surrounding will be increasing. So, now let us look at the heat transfer that is happening. From the surrounding point of view, what are the amount of energy the surrounding is losing? Before going to that, let us give some names to this. Let us say the evaporator is working at a temperature level of TE, condenser at temperature TC, generator is working at a temperature of TG, and evaporation the absorber is working at a temperature of TA. So, how much energy the surrounding is losing? Q dot E and Q dot G are getting added to the system, that is coming out of the surrounding. So, it is losing entropy in that form, Q dot E by delta T. I should have put a dot here just to represent that we are talking about the rated quantities. So, we can write this as Q dot G by Tg, and this should have been Te, plus it is adding heat in the form of Q dot A by Ta plus Q dot C by Tc. This combination has to be greater or equal to 0, because both Q dot A and Q dot C are going to the surrounding. Now, for most of the practical situations, we generally have T and Tc to be equal to each other. In all practical systems, generally we have the same situations. So, we replace this Tc, or rather this Ta with Tc. Now, we combine the first law with this, Q dot E by Te minus Q dot G by Tg, and combining this first law expression from here, we can write this 1 by Tc into Q dot E plus Q dot G minus W dot P to be greater or equal to 0, or combining Q dot E together, 1 by Tc minus 1 by Te plus Q dot E sorry, I should have written Q dot G here. So, Q dot G is 1 by Tc minus 1 by Tg minus W dot P upon Tc greater or equal to 0. Now, the pump work, the magnitude of this one generally is very small compared to all this heat interaction, the Q dot E and Q dot G particularly. So, let us remove this one from this. So, if we now reorient the terms, so we can write that Q dot G into 1 by Tc minus 1 by Tg is greater or equal to Q dot E into 1 by Te minus 1 by Tc, or Q dot G into Tg Tc into Tg minus Tc is greater than Q dot E into Te Tc into Tc minus Te, and finally removing Tc from here. If we write that, if we reorient the terms once more, then we can write that this Tg minus Tc upon Tg into Te upon Tc minus Te, this quantity is greater equal to Q dot E upon Q dot G. But why we are doing all this derivation? Because if we think about a compression based cycle, a vapor compression cycle working between the same temperature limits of Te and Tc, then what would be its COP? COP of an equivalent vapor compression cycle, the maximum value should be equal to the corresponding Carnot refrigeration cycle COP, which is nothing but Te upon Tc minus Te. So, this is the maximum COP of an equivalent VCRS system can have, and the VRS that we are talking about, if this cycle is completely reversible, then it is going to have the maximum COP, and if the cycle is completely reversible, then the rate of entropy generation also will be equal to 0. In that case, it is what will be a COP? So, COP for this VARS max will be, now the normal definition of COP for this case is the refrigeration effect divided by total energy input that you are giving, which is Q dot G plus W dot P. Again W dot P being very small, let us remove this one. So, it is Q dot E upon Q dot G, that is the COP always, and when we are talking about the maximum COP, then delta S surrounding will be equal to 0, and then picking up from there we can say that this will be equal to Tg minus Tc upon Tg into Te upon Tc minus Te. So, COP for the VARS max divided by COP for the VCRS max, then what it will be? Just dividing this expression with the COP for the equivalent VCRS, we have Tg minus Tc upon Tg, which is always less than 1, and therefore, COP for the VARS is always less than 1, because Tg always operates a temperature much higher than the condenser or evaporator temperature, and therefore, COP for the absorption system always will be much lower compared to the equivalent compression system, and that is a primary reason of the absorption system, despite being a very classical design, is not the most popular one. It is not the most popular one simply because of its low COP. If we take a quick example, let us take a situation where your Tg is equal to 100 degree Celsius, which is something like, which is a quite practicable value. So, it is 373 Kelvin. Let us say Tc is the atmospheric temperature, which is 27 degree Celsius. So, 300 Kelvin, and we take a T of let us take 0 degree Celsius. So, which is just 27 Kelvin. So, what will be the COP for corresponding VCRS, the maximum COP? So, maximum COP will be Te by Tc minus Te, which is so Te in this case is COP for the equivalent VCRS is Te, which is 273 Kelvin divided by Tc minus T is approximately 27. So, it is roughly equal to 10. Similarly, COP for the equivalent VARS max. So, where the additional factor of Tg minus Tc upon Tg is coming into picture. So, if you calculate, it may be roughly equal to just 2. So, it is only 1/5, and practically the COP of VRS system, this is the maximum one, is always of the order of 1 or maybe even less than 1. So, the absorption system, despite being a very less work input requirement, is not something that is going to give a very high COP. Only if you have a source available of very large quantity of thermal energy, then only the absorption system becomes very productive, because then we can use the waste energy and run the system almost without any mechanical energy input. In that case only the absorption system is economical, and that is why we generally use the absorption system for large scale application with some source of low cost large quantity of waste heat, something, or maybe just renewable energy sources like solar energy. Some of the desirable properties that we need to have for the working fluids that we use, the refrigerant and absorbent combination must have a good miscibility with each other over the entire range of working conditions. No way they should get separated from each other. The heat of mixing should be as small as possible, so that the QA remains small. They should not solidify during the system. That is one problem with water based systems, because if the temperature falls below 0 degree Celsius, then water becomes solid, and that is why water based systems like the water lithium bromide system is not used below 0 degree Celsius. Its application is restricted only to above 0 degree Celsius, that is primarily to air conditioning application, whereas ammonia can easily go to -15, -20 degree Celsius. So, ammonia based system is more commonly used for large scale refrigeration. They should have good chemical stability over the entire range of operation. Viscosity should be low, so that there is very small frictional losses, pump work input requirement is less, and also the thermal conductivity should be high to have a good heat transfer characteristic, and they should also be non corrosive to the metals that are being used. If let us quickly try to analyze one water lithium bromide based absorption system. The cycle is shown here. Here you have the condenser, generator, evaporator and absorber, their temperatures and corresponding heat interactions are given. Look at the this dotted line. Above this we have the condenser pressure, below this we have the evaporator pressure. The solution pump is the one that is rising the pressure, whereas we have two expansion valves, one corresponding to the refrigerant, other corresponding to the mixture, where we are using the expansion valves to lower the pressure. And also this line separates the refrigerant and the mixtures. Let us assume the refrigerant flow rate to be equal to m dot. Now, there are two mixtures. So, we commonly call one mixture to be a strong solution, the one having larger fraction of refrigerant, other we call a weak solution. So, here out of the two lines, which one is going to be having a higher concentration of the refrigerant? Remember, the refrigerant is water in this case. The one going from absorber to generator definitely has more water content. So, this one we are calling m dot strong solution, whereas this one we are calling m dot weak solution. So, let us try to analyze it quickly, but for that we are assuming all the frictional losses to be negligible. Solutions leaving generator and absorber are in equilibrium. That is an important assumption, because that allows us to calculate the absorber and generator, the mixture qualities that are leaving the absorber and generator. Solution pump is assumed to be adiabatic, and only pure water vapor is produced in the generator. With these assumptions, if we quickly do the analysis starting from the condenser, so we can write Q dot C is equal to m dot into H1 minus H2, and whatever mass is entering, that is leaving. For the expansion valve, let us call this one to be refrigerant side expansion valve, and this one we are calling the solution side expansion valve, as there are two expansion valves. So, this is for the condenser, and for the refrigerant expansion valve we can easily write H2 equal to H3. This is for the refrigerant expansion valve. Then for the evaporator we can write Q dot E to be equal to m dot into H4 minus H3. This is for the evaporator. Commonly we are aware about the temperature levels, because T is something that is determined by our target application. Tc depends on the surrounding condition, and Tc and T are generally equal to each other, and generator temperature that generally requires some kind of optimization, but still it depends more on the temperature of the source that we are using. And the Q dot E also has to be known, because that is the refrigerant load that we are talking about. So, using this we can easily calculate the mass flow rate for the refrigerant that is flowing through this. Now, coming to the absorber, in the absorber there are 3 lines. So, total amount of energy that is entering this is m dot H4 plus m dot weak solution into H10, and that is leaving is Q dot A plus m dot strong solution into H5. This is for the absorber. So, by rearranging the terms, we can write Q dot A to be equal to m dot into H4 plus m dot weak solution into H10 minus m dot strong solution into H5. Now, if we perform a mass balance across the absorber, then what we can write? M dot weak solution plus mass flow rate for the refrigerant should be equal to m dot strong solution. And now, what is the mass flow rate of weak solution? M dot weak solution is actually that actually depends upon the concentration of the lithium bromide that we are using. The amount of lithium bromide that remains the same, is not it? The amount of lithium bromide that was there in the weak solution, the same lithium bromide remains in the strong solution as well, because lithium bromide actually is a solid that just get dissolved in the water. So, if X represents the mass fraction of the lithium bromide, then the mass of lithium bromide that is there in the weak solution can be written as X weak solution into m dot weak solution, and the mass of lithium bromide that is present in the strong solution will be X strong solution into m dot strong solution, where X again represents the mass fraction. So, from there we can easily calculate the mass of each of the solutions. And how to calculate the X? The X depends upon the temperature of this the absorber temperature. So, as we have assumed the solutions leaving the heat exchangers to be in equilibrium. So, your X for the strong solution actually will be a function of the absorber temperature, and X for the weak solution will be a function of the compartment that is it is leaving, which is the generator temperature. So, from there we can easily calculate the mass fractions for, or the mass fractions for water and lithium bromide in the both the lines, and accordingly we can get the value of the energy content. Similarly, we can, if we perform an energy balance across the generator, then total energy that is coming in is m dot strong solution H7 plus Q dot G is equal to m dot into H1 plus m dot weak solution into H8, or rearranging we can write Q dot G to be equal to m dot into H1 plus m dot weak solution into H8 minus m dot strong solution into H7. This is for the generator. Also, we have the pump. So, for the across the pump we can write the solution pump, the total pump work that you are giving as input is equal to m dot strong solution into, look at the state points, it is 6 and 5. So, it is into H6 minus H5. The solution side expansion valve, it is again an isenthalpic valve because we are assuming it to adiabatic. So, it is H9 equal to H10, and finally, we have the heat exchanger. So, the amount of energy exchanged across the heat exchanger, that has to be equal if it is an ideal heat exchanger. So, across the heat exchanger we can write mass flow rate for the strong solution into the amount of energy it has gained, that is H7 minus H6, is equal to amount of energy lost by the weak solution, that is H8 minus H9. Quite often we need to have one parameter which characterizes the performance of the heat exchanger, which is given as the effectiveness for this heat exchanger, and this effectiveness is defined as the maximum possible temperature change that the weak solution attains, the actual temperature change the weak solution attains divided by the maximum possible temperature change. The actual temperature change is happening from 0.8 to 0.9, that is from generator temperature to 0.9. So, the change is Tg minus T9, and what is the maximum possible change in temperature that is that can happen, that is Tg minus Ta. quite often the effectiveness is provided by the manufacturer, and as Tg and Ta are known, so we can calculate T9 from this and accordingly can perform the energy balance across the heat exchanger. And finally, we get the COP for this cycle as Q dot E divided by Q dot G plus W dot P. Quite often the pump work can also be neglected from this. So, this is the way we can analyze an absorption refrigeration cycle. Now, though we have talked about the water lithium bromide system, but that has certain issues to be talked about, like there can be crystallization problem. If the temperature particularly in the evaporator drops below certain limits, as its pressure drops, then lithium bromide, which is actually a solid, can get separated from the mixture and can get deposited in the form of crystal, which can lead to severe blockage issues. So, there are certain limits below which we can't lower the temperature. Then there can be air leakage problem. The water lithium bromide system always works under sub-atmospheric condition at both condenser and absorber and also in the evaporator. Therefore, it is possible that air can leak into the system, and we have to be very careful to protect from this air leakage, protect the system from air leakage, though it is not, it can't be avoided completely, only by frequent maintenance maybe we can get rid of this or eliminate its effect. There can be pressure drop, as the solid solution of lithium bromide is flowing through these mixer side lines, there can be significant amount of pressure drop. So, additional work for the solution pumps, and also the constraint on the low temperature, as we are using water as the refrigerant. So, we can't go very close to 0 degree Celsius, and therefore, its application is restricted only to air conditioning purpose. And that point ammonia water mixture is very much advantageous, because it can achieve very low temperatures, can easily go to -15, -20 degree Celsius. So, very suitable for large scale refrigeration. There is no air leakage because the pressure always remains above atmospheric. There is no crystallization problem as well, because ammonia is a vapor only, but ammonia has its own issues. Like ammonia is toxic, that is one big problem, and that is something that has restricted its use, particularly in big applications like cold storage, etc. But again I should mention that ammonia has the advantage that it is cheaper compared to that water lithium bromide solution. So, if you are looking for a very big application like cold storage, probably we would go for ammonia vapor, despite having its own problem. Like there is temperature glide in the condenser, like when ammonia vaporizes in the generator and tries to go to the condenser, there it will always be mixed with some water vapor. So, we need some rectifiers, some deflagmator columns, etc., to remove the water vapor from that mixture and allow only pure ammonia to go into the condenser. But still that process is never 100% foolproof, and that is why some water vapor is always likely to enter the condenser, thereby severely affecting the performance. The temperature glide refers to that we may not be able to maintain that isothermal condition, there will be some temperature change during the condensation process. And because of that, heat transfer performance also will be inferior. Incomplete evaporation, as I have just mentioned, some liquids may enter along with the water vapor. When it passes through the expansion valve, it gets condensed to form some liquid water, and during the evaporation process, while ammonia evaporates, that water vapor may remain as in the liquid form, affecting the evaporation process, and again the heat transfer characteristic. And in order to remove all these things, the system becomes much bulkier and costlier compared to water lithium bromide. So, finally, we would like to quickly compare the absorption and the compression based systems. The first criteria is based on working. So, the compression based systems are work operated, because we are giving mechanical energy as the input, whereas this is heat operated, though mechanical energy is required in the pump, but primary input is in the form of heat in the generator. Then COP is definitely much higher COP we get compared to the absorption system. Then dependence on TE, the performance is very sensitive. Any changes in the evaporation temperature, the COP and other performance of compression refrigeration system gets affected very strongly, whereas it is virtually independent. It is virtually independent on the evaporation temperature. Then the evaporator exit state. The evaporator exit state as after evaporator it is going to pass through a condenser, pass through the compressor, so must be vapor. We have to ensure that in the evaporator we have at least saturated vapor or preferably superheated vapor leaving and going to the compressor. But in the absorption system it is finally going to the absorber, so it can be liquid also. We always want this to be vapor, but even if some liquid enters the absorber, there is no issue. So, it is much safer from that point of view. Part load performance, part load refers to means whenever you design a system, we design for the maximum load or full load, but quite often we may have to run the system under part load condition. Like suppose your domestic refrigerator is has been designed so that it can simultaneously cool 50 kg of vegetables, but at a particular instant of time there may be just 1 kg under this. So, that is running under part load condition. So, part load performance for VCRS is poor, but this is more or less unaffected. Over a wide range of load situation, its performance more or less remains the same, and that is why it is very much preferred for large scale application. Like in a shopping mall, you may have designed the air conditioning systems assuming that there will be 500 persons inside this simultaneously, but even if there are 50 persons, its performance may not be affected, whereas for compression refrigeration system the performance will be very much inferior. Compactness, now for small capacity system, smaller systems are more compact, whereas here the larger systems are more compact, because here we have two additional compartments in the form of absorber and generator. So, when you are talking about a smaller system, the system may be quite bulky compared to an equivalent VCRS. Working fluid, primarily we are using synthetic fluid here, synthetic refrigerants, whereas here we are using natural refrigerant in the form of ammonia or water vapor. And finally, the economical point of view, this is generally economic and also available over large range of sizes, but it is economic only when some waste heat is available. Other if some source of waste heat is not available, then it is not economic at all, and that is why VRS is more preferred for large scale application because of this. So, that takes us to the end of this particular module, where we have talked about the concept of refrigeration, discussed about different applications, different methods of producing low temperatures. Then we talked in detail about the compression based system, starting with the reverse Carnot cycle and then the vapor compression refrigeration cycle, different variations of that. Then we briefly talked about the gas refrigeration cycle, and today we have talked about the absorption refrigeration cycle, its primary characteristics and also compared with the compression cycle. So, we now know that while we prefer the compression based cycles for small scale application or small to large scale application, absorption based systems are more preferred for large scale applications. So, that takes us to the end of week number 9. The assignments will be available soon. So, you please solve the assignments, and if you have any query, please write back to me. Refrigeration is a huge subject, often taught as separate subjects and the final year as a final year elective or at master degree level, and a very interesting and practical subjects as well. So, if any of you have further interest, please refer to textbooks. There are several very good textbooks are available purely on refrigeration. Thank you.